Hello everyone, in this video I would like to show you how you can solve the inverse dynamics problem for planar tooling RP robot arm. RP basically means that the first joint is a rotational joint and the second one is a prismatic joint. So we have rotation here and translation over here. Okay, so we're going to be using Python just like before, and mainly two Python libraries. First of them is SymPy, which is for like symbolic math, and the other one is NumPy, which is more like for numerical calculations, and matplotlib for some plotting. Also have a helper function here so that I can display some of the results in a nice way. Okay, so here we have the kinematic scheme of our structure. As I said before, we have rotation, we have translation here. We also have two centers of mass, and they're located somewhere halfway, the first link and also the second link. And also we have this variable parameter here, lambda, which basically goes from the beginning of our coordinates, or the origin of our coordinate system, all the way up to M2. And L1 is the distance from the origin of our coordinate system to the first center of mass. And this angle theta here is basically the angle between the horizontal x-axis and the first link, and by extension also the second link. Okay, so the first step is to define all the necessary symbols and functions. So M1 obviously, M2 for those centers of mass, L1 is this distance, L2 is this distance, G corresponds to the gravitational acceleration. Then you have T, which stands for time, and basically those are the symbols that we're using. And we also have something called dynamic symbols, and these are like functions of time. So this is going to be TH for theta and LA for lambda. So this is how we define them. And the next step is to define the positions of the centers of mass based on the angle and the extension of this second link. Okay, so this is just pure math. Well, before we go here, let's just run those cells. Okay, so we define the positions of the centers of mass based on the angle and the extension, as I said before. So here's just L1 times cosine theta divided by 2, because we're treating those as slender rods. So the center of mass by default is located halfway the length of each link. So here it's similar. We have L1 times sine of theta divided by 2. As for the other one, just have lambda times cosine theta, and y2 is lambda times sine theta. So let's run this, and here you see the results in a nicer form. So the next step is to differentiate the positions with respect to time. So we using the method or the function inside the SymPy library, or this module, and we specify that we want to do it with respect to time. So we're using this T symbol, and we do pretty much the same thing for all of those. So we can get the horizontal as well as the vertical components of the instantaneous velocity of those centers of mass. So here's what it looks like. So now we have that. We can introduce some shorthands for derivatives. So instead of writing derivative theta with respect to t, and then again derivative of theta dot with respect to t, or derivative of lambda with respect to t, or lambda dot with respect to t, we just use those shorter symbols. So let's run this as well. And since we're just like before, we're using the Lagrangian approach, we'll be calculating the kinetic and potential energies. So we need the total kinetic energy for the system as well as the total potential energy for the system. So basically we're splitting those energies into two components as far as the kinetic energy goes. So we have the first mass times x1 dot squared plus y1 dot squared. Divide everything by 2 because remember we have 1 over 2 in the formula. And then you have the rotational component. So basically we're using the moment of inertia for a slender rod, which in this case is basically m times L squared by 12, but in the end it's by 24 because of the fraction that we have in the formula, which is 1 over 2. Okay, and in the case of the second kinetic energy, it's very similar. You basically just need to change those numbers here, or those indices. Okay, so as for the potential energy, it's pretty simple as well. So just use the distance, by projecting this distance onto the vertical y-axis. So this is m1 times g times y1, and the second potential energy is m2 times g times y2. So we also display those energies here. And this is what it looks like. The next step is to write down the Lagrangian function, or in this case, we basically add those energies. So the total kinetic energy minus the total potential energy. So let's see. This is what it looks like. And then we can use the Lagrange's method class and the method inside that class from Lagrange's equations to derive the equations of motion, which look like this. Okay, so now we're kind of done with the symbolic part, using SymPy basically. Now we go over to NumPy. So the first thing to do is to turn the equations of motion into functions that take numerical values. So basically we take these functions, or those equations rather, the one for t and the one for f, and we make them accept numerical values. So it can be either, just a single value, or it can be like an array or a list of values. So in this case, you will have multiple values here, for example, for theta, because normally you will analyze it over a specific period of time. So you have to have more than one value. Same for the first derivative of theta, the second, lambda, and then the first derivative and the second derivative of lambda. Okay, so speaking of lambda, we use a function called lambdify that is inside this utilities module within SymPy. So it takes those parameters here, and this is the first equation with the 0 index, and the second equation. So this is how we turn them into those equations, or those functions that accept numerical values. So of course we have to introduce those values as well. You have to assume some M1, M2, L1, L2, and G. I'm using capital letters here to differentiate between the symbolic values as well as the numerical ones. So okay, that's what we have here. And now we're gonna assume some general shape of the trajectory. So let's imagine that the tip of the second link moves along some specified path. So maybe something like this. But basically it starts somewhere, it performs some kind of movement, and it stops at another point. Okay, so this is what we have here. So it just basically using the sine function and cosine function and sine function again to get something that looks like this. It doesn't necessarily have to be this, but it's just an example. It doesn't really matter because you can replace it with anything else you want to have there, and it can work just fine. But as you can see here, it's from 0 to 10, and here from minus to up to 1. But you know, we've assumed some dimensions here for those links. So of course, the work area, I'm speaking of the work area here because it's a planar structure rather than, you know, a 3D structure. So I'm not really talking about a workspace. So coming back here, we have to make sure that all of the points of this trajectory can be reached by the tip of the second link, right? So we assume some rectangle inside the this work area. So for example, maybe something like this. So at a certain angle we have the left bottom corner, then we have the right bottom corner, top left corner, and top right corner for this trajectory. And this is exactly what we're doing. We're assuming some angle. In this case it's just 30 degrees, so pi over 6. So we calculate those extreme values, so x minimum, and then y minimum, x maximum, and y maximum. Yeah, so this defines the rectangle that we want to keep our trajectory in. So now we have to fit that trajectory into that rectangle. So this is just a helper function that lets us do that. So we run the trajectory that we initially prepared here in terms of its shape through this fit function. Okay, so let's see what it actually looks like. Right, so as you can see, it's pretty much the same shape. It just kind of stretched or squeezed in, well, stretched in along the x-axis and squeezed along the y-axis. So this is what it looks like now. Okay, but the trajectory specifies the consecutive positions of the tip of the last link. So we have to convert those positions to the joint variables. So we have to perform some sort of conversion from the trajectory points to the joint variables. In this case, this is very simple. We're using some simple trigonometric relationships here to do that. Okay, so this is our theta, this is our lambda. Once again, I'm using capital letters here to distinguish them from the symbolic variables, right? So here I'm using the arctangent function, and here I'm using the basically the Pythagorean theorem to get the value of LA, which in this case is lambda. So let's run this. And before we proceed to a numerical differentiation, we have this interpolate function that I presented to you in one of my previous videos. So basically, as we perform numerical differentiation, every time we do it, we lose one element. So, so if you have, like, let's say 1,000 elements, or 100, let's say 100 elements, then after differentiating once, you get 99 elements, and so on and so forth. So in order to make up for that loss, we use that interpolate function to get the same number of elements, because when we want to use this lambdified function, we have to provide the same number of elements for each of those parameters, right? So that's why. So here we just quickly calculated t, which is like the time step. So we just calculated as the difference between the second element of this simulation time and the first element. Okay, so let's run this, and then we can proceed to calculate the required torque on the first link and the required force on the second link to set this whole structure in motion, and in such a way that the tip of the second link moves along the trajectory path. So let's run this part as well, and let's plot the torque. Right, so this is what it looks like. So we have time over here from 0 to 10 seconds, just like we defined here, using the Linspace function from the NumPy library. Okay, so this is the this is what the torque looks like for this trajectory. And let's also plot the force. And here's the force. Yeah, so basically that's it when it comes to the inverse dynamics, because the whole problem is to find the torques, the forces that are required to set your structure in motion in such a way that the last link, or maybe the end effector, will go along some specified path, some trajectory. This is the whole idea here, and this is how you can do it in Python. So I hope you find this video useful. If you do, please leave a comment, like it, subscribe to my channel, so I can continue making such videos, and not only such videos, but different types of videos on programming. Okay, so if you have any questions, leave a comment as well. I'll try to answer. And hopefully see you next time. Bye.